For this problem, we are asked to find all values of x where the tangent line to the given function is horizontal. If you recall, the slopes of a tangent line are represented by the derivative, and a horizontal line has a slope of 0. So basically what we're asked here is to figure out when is f prime of x going to be 0. So the first thing we should do is use the rules that we just talked about to find the derivative. So if we want to find the derivative of f, we're going to have f prime of x equals. So the power rule says take 3, multiply by 2 to get 6, x to the 1 power less, so 6x squared. 9 times 2, that's going to be 18 times x to the first, right, subtracting 1. Minus 60 times 1, so that's going to be 60. And then x to the 0 is just 1, so we have this. So we want to know when is this equal to 0. So 6x squared plus 18x, 18x minus 60. When is this equal to 0? I can actually divide everything by 6 to make my life a little bit easier. So I'm going to get x squared plus 3x minus 10. And this is factorable. So if I factor this, I get x plus 5, and I get x minus 2. Setting each of those pieces equal to 0, I can get that x equals negative 5 and x equals positive 2. So those are the two values of x that give me a derivative that is 0. So that means that the slopes of my tangent lines will be horizontal, or the slopes of my tangent lines will be 0, meaning the tangent lines are horizontal at x equals negative 5 and at x equals 2. When we're talking about derivatives, often we are talking about a rate of change, right? Because if we're saying that the derivative represents the slope of our tangent line, we know that slopes are just a rate of change. So one common use for the rate of change is also to describe the motion of some object that's moving in space. So if we're trying to talk about the motion of an object, we use some function called the position function, and it's represented with the variable s. And basically what it does is it tells us the position of whatever our object is that's moving, where it's located relative to the origin as a function of time. So if we are given this formula that we know, rate equals distance divided by time, then we can say that the average velocity is represented by the change in the distance divided by the change in the time. Remember where s is representing the position of our object, right? S is the position. So the change in our position divided by the change in time that we're comparing that position change. So let's look at some applications of this type of problem. So in this problem, we have a tennis ball that's being dropped from a height of 150 feet. The ball's height s, so that's the position of the ball, at time t is represented by this position function. S equals negative 16t squared plus 150. S is measured in feet, and time is being measured in seconds, which means we're going to be dealing with feet per second as our velocity, the average velocity. So if I want to find the average velocity on the interval from 2 to 3 seconds, first we evaluate our function s at time 3, and we subtract the value of our function s at time 2. Because this is going to represent my position after 3 seconds, this is going to represent my position after 2 seconds, and we want to know the difference between those. And then to find the difference in time, we just take their difference, 3 minus 2. So we're going to substitute this information in to our function s. So we're going to get negative 16. 3 squared is 9, so negative 16 times 9, plus 150 minus negative 16 times 2 squared, which is 4, plus 150. All of this divided by 1. Doing some algebra, we're going to get negative 16 times 9, or some arithmetic. Negative 16 times 9 is negative 144 plus 150. This is going to be negative 64, but times the negative is going to be positive 64. And then distributing the negative gives us negative 150. All of this is being divided by 1. We can see that we have these 150s that will cancel, and negative 144 plus 64, that is negative 80 feet per second. Now, the reason why my velocity is negative is because velocity has direction. It represents direction. And since the ball is falling, right, its height is decreasing, that's what the negative represents, is our ball falling through the air. So let's try the next one. So we're going to do the exact same process. We're going to evaluate our function at 2.5 and evaluate our function at 2, taking their differences because we want to know how much their position has changed during those times, and then subtract the time to find that change. So doing this, we get negative 16 times 6.25 plus 150. And then all of this, we've already seen, it turns out to be plus 64 minus 150 because we're subtracting the same amount each time. And then this is all divided by 2.5 minus 2 is 0.5. Negative 16 times 6.25, that is negative 100. So negative 100, the 150s are going to cancel, so plus 64, all divided by 1/2. Negative 100 plus 64, that's negative 36. Negative 36 divided by 1/2 is going to be negative 72 feet per second. It's really important that you include the units because we want to know what we're talking about when we do these problems. And then the last one, we're going to evaluate the same way. So at 2.1, we're going to evaluate our function, and then at 2. So at 2.1, we get negative 16 times 4.41 plus 150, and then we know again that this is going to be plus 64 minus 150. All of this is now being divided by, this is being divided by 2.1 minus 2. So 2.1 minus 2 is 0.1. So all that's being divided by 0.1. Negative 16 times 4.41, that's negative 70.56. Negative 70.56. The 150s are going to cancel. So plus 64, all divided by 0.1. 70.56 plus 64, negative 70.56 plus 64 is negative 6.56. And then dividing that by 1/10 means we're going to multiply by 10 to get negative 65.6. And then again, it's feet per second. So these would be the velocities, the average velocities over the different intervals. And you can see that as the interval is decreasing, the average velocity it's slowing down just a little bit. In the last example, we talked about the average velocity, and we used at a difference quotient that looked very similar to our average rate of change. So in this next example, we're going to use something called the instantaneous velocity. And the instantaneous velocity, sometimes it's referred to as the simple velocity, is just the derivative of our position function. So if you have some position function s, if you take its derivative, that we can use that to find the velocity of our moving object at a specific time. The velocity describes both speed and direction that an object travels. So because of that, we saw in that example we had some negative velocities, and that was meaning that that our object was falling. It was getting closer to the ground. So the difference between velocity and speed, speed is just the absolute value of the velocity of an object. So if we have this position function, s of t equals 1/2 g times t squared plus v sub 0 t plus s sub 0, this is the general position function. The g represents the gravity constant. It's about negative 32 feet per second squared. And in meters, it's about negative 9.8 meters per second. This is our initial velocity. And then this is our initial position, or the starting height of our object. So let's go ahead and take a look at some examples using the instantaneous velocity. So in this example, we have a water balloon that is thrown upward from the top of an 80-foot building with an initial velocity of 64 feet per second. If the height s in feet of the balloon can be modeled by this position function, where t represents the time in seconds after it was thrown, we want to know how long is the water balloon in the air, what is the velocity of the water balloon when it hits the ground, and what is the speed of the water balloon when it hits the ground. So if we want to know how long the water balloon is in the air, basically we want to figure out when does it hit the ground. So that means that its position, or its height, would be 0. So we can kind of sketch a little picture here. So if we have this here, so we have like a water balloon, it's being thrown up in the air and it's coming down like this. That's really bad. Sorry. Being thrown up in the air and coming down something like this. If I want to know how long it's in the air, I want to know right when it's hitting the ground. And that means my position would be 0. So I want s of t to equal 0. So plugging 0 in, I get negative 16t squared, or not plugging 0 in, but making s of t 0. Negative 16t squared plus 64t plus 80 equals 0. All of these are divisible by 16, so I'm actually going to divide everything by negative 16, giving me t squared minus 4t minus 5 equals 0. If we factor this, we get t minus 5 times t plus 1 equals 0, giving us a time of 5 and negative 1. Now clearly negative 1 doesn't work because we can't have a negative time. So after 5 seconds, the ball will hit the ground. So it is the balloon is in the air for 5 seconds. So the balloon's in the air for 5 seconds. That's after 5 seconds, we'll see that it hits the ground. So to find the velocity, we said the velocity is represented by the derivative of our function. So we want to know what is s prime of t. So finding the derivative, we're going to use the power rule. So that's going to give me negative 32t to the first plus 64. And I want to know what is the average, or what is the velocity at time 5. So what is s prime of 5? So plugging that in, we get negative 32 times 5 plus 64. This is going to be negative 160. And then plus 64 is going to be negative 96 feet per second squared. So the velocity is going to be that's feet per second. Negative 96 feet per second. And if I'm asked to find the speed of the water balloon when it hits the ground, the speed is just going to be the absolute value. So the speed is just going to be 96 feet per second because we just take the absolute value of negative 96.